All right. Hello, class. Good afternoon. Um, so, I apologize for starting my lesson later than usual and then also starting it later than I said I was going to start it. Um, on Wednesdays and Sundays, I do uh, a, a longer, more intense run, and so it took more time. And then I cut my hair, and uh, and then I took a long shower. And I'm a person who takes a long shower, so what can I say? I'm here with Hazel. Can you see Hazel? Uh, she is, since the weather has kind of turned around, it just kind of puts her to sleep, the heat. Hey, Rourke. Hey, Theo. Um, so, you might have noticed that we have just been doing some random topics. On Monday, we discussed, what did we discuss Monday? Oh, we discussed linearizing graphs. And then on Tuesday, we discussed um, tension and wave speed. Hey, Camille. Hey, Simon. Hey, Matthew. Hey, Matthew, you have a really cool icon for Google. Your Google icon with Emperor Palpatine. I like that icon. Um, so yeah, we're just kind of doing some random topics that are finishing out the curriculum. Um, so today's lesson is going to be unrelated to yesterday's lesson, which was unrelated to Monday's lesson. And it's not going to have anything to do with tomorrow's lesson. So it's just the last few topics. Um, hey, Camille, I'd be curious to know how, since you're watching, I'd be curious to know how your choir class is going, what that's like. I don't know. Send me a DM on Discord or Remind or something, because I'd be curious to know what that's like. Um, all right. So this is going to be an easy lesson because I think you guys already know about this topic. You've already learned about it before. Um, we're going to talk about density. So this should be a pretty quick lesson because I think you guys already know about it. Density is denoted by the Greek letter rho, and it is defined as the mass of an object divided by the volume of the object. So density is mass per volume. Now, the equation that you would use for volume is going to depend on a number of things. It's just going to depend on what kind of shape it is, right? If it's a sphere, you might use 4/3 pi r cubed. If it's a rectangular prism, you might use length times width times height. If it's a cylinder, you might use pi r squared times the height. So it just kind of depends on what shape you're using. The units of density are kilograms per cubic meter. All right. I'm going to give you a couple of densities. You don't have to memorize these densities. Actually, there's one density that I do want you to memorize, and that's the density of water. The density of water is 1,000 kilograms per cubic meter. All right. That's fresh water. The density of salt water is slightly more. It's 1,025. Depends on salinity. Another density that I find useful is the density of air. The density of air also depends on humidity. It depends on temperature, because if the air is hot, it expands and it's less dense. But if you were to just pick what's a ballpark value for the density of air, it's about 1.2 kilograms per cubic meter. And then things like rocks. Rocks have a wide range of densities because they're made out of a lot of different minerals, okay? But if you just wanted a ballpark, what is the density of rock? It could be anywhere from, 3,000 up to 9,000 kilograms per cubic meter. It's more dense than water because rocks sink. Okay. So, one of the things I want to talk about, the AP just wants you to know what density is, but one of the things I've noticed that AP asks about is they might ask you to rewrite something in terms of density. Okay? So I'm going to do an example. So you might remember the equation for the gravitational field on an alien planet. Little g is equal to big G times big M over r squared, where M is the mass of the planet and r is the radius of the planet. So this is the acceleration due to gravity if you're standing on the surface of the planet. And so we could ask the question, well, what happens if the planet were made bigger? And you might say, well, gee, that would decrease, or that would increase the radius of the planet, so you might expect gravity to go down. But if you make a planet bigger, you're building it out of more material, so its mass also increases. Okay? So if we want to know what's going to happen when we make this, the planet bigger, we should probably write it in terms of density. Because if we add more layers of rock, all the rock has the same density, right? So we're not changing the density, but we are changing the radius. And we're changing the mass by making the planet bigger. So one of the things we can do is we can take this equation, density equals mass per volume, and we can multiply both sides by volume. So mass equals density times volume. Okay? Planets are roughly spherical. They're not exactly spherical, but we can assume that they're spherical. This lesson is brought to you by Milk Tea, by the way. So the volume of a sphere is 4/3 pi r cubed. Okay? So then what I'm going to do is I'm going to take this formula for mass and I'm going to plug it in for mass here. And I get G times density times 4/3 pi r cubed over r squared. Now you can see we have an r cubed over an r squared. And so that's just going to give us a factor of r. So we would get 4/3 pi g rho r. So that's our final answer. So one of the things that's interesting about this is what it says is as long as we keep the density of the planet constant, which is a reasonable assumption because if we make a planet bigger, we're piling on more layers of rock that all has the same density, okay? So for a fixed density, meaning we're making the planet bigger out of the same material, as we increase the size of the planet, the gravity goes up. Okay? So basically what that means is that the mass increases a lot faster than r squared increases, so that the overall gravity goes up. I read an interesting article which said that if the Earth were any bigger than it is currently, you would have a bigger R value for the Earth, which means that gravity would be greater than 10 meters per second squared. And if gravity was greater than 10 meters per second squared, it would mean that a lot of things would be more difficult for us. It would be more difficult to make buildings that don't collapse because everything would have more weight. It would be more difficult to get into space because you have to overcome gravity to get into space. And basically, if the Earth were any bigger than it is, our technology would basically be stunted as a result of that. We would probably all be shorter too. All right. I'll do one more example. Let's suppose you manufacture need some more tea. A cylinder out of wood. No, I don't want to make it out of wood. Let's make it out of. Let's make it out of iron. Okay, and I'm going to draw a picture of the cylinder. All right. Man, my computer's really working right now. I think I got too many windows open. Let me close some windows here so my computer doesn't explode. Ah, I found it. Okay. So let's suppose that the cylinder is 3 meters long. And let's suppose that the cylinder has a radius of 0.25 meters. Okay? So what I'm going to do is I'm going to look up the density of iron. Okay? I'm going to assume it's metallic iron because, you know, even if something is made out of, you say it's made out of iron, well, there's different preparations of iron. It's like if something is made out of carbon, for example, you know that graphite is carbon, but then also diamond is carbon. So there's like completely different versions of, they'd say, allotropes of carbon. So I'm going to look up, say this is metallic iron, because that's going to be more specific. So I'll look up density of metallic iron. And I'm not showing you this. The density of metallic iron is 7,900 kilograms per cubic meter. Okay? So, if I want to know the mass of this cylinder, mass would be density times volume, which would be, this is a cylindrical shape, so I'm going to use the equation for volume of a cylinder. Density times pi r squared h. And then I just plug in numbers. 7,900 times pi times r squared, so 0.25 squared, times h, which is 3. The cylinder's sideways, so its height is its width, I guess. Plug that in. And I get that this iron log would have a mass of 4,600 kilograms, approximately. Quite heavy. We could do another, I'm not even going to do it, the problem, but just to give you an idea, we could also give you the mass of the object and its dimensions, and you could calculate the density. So this equation works all different ways. That's my lesson for today. I hope you guys are well. I would love to hear from you, just how you're doing. A lot of you are in the homework are just saying good or great when I ask how you're doing. So, you know, if you want to send me a DM and tell me how you're doing, I'd love to hear from you. So me and Hazel are saying bye-bye.